Thank you, Zoom robot, Mrs. Voice. It's wonderful to be back. Second session of Outsmarting contracts. We'll be looking again at Ethernauts and going through a little bit more in depth the actual Solidity and discussing how the code is structured, what a smart contract really looks like, and how to attack these things. In particular, using some other contracts. That's going to be the focus of our session today, because that's the majority of what actually happens out in the wild on mainnet is not people doing what we did last time, which was mostly interacting with smart contracts through a web page from our JavaScript console, but rather actually writing contracts themselves and having a go. You could make sure that you're on mute. That would be good. Thank you very much. So yeah, the majority of hacks and attacks that actually happen on the main network are not what we did last time, which primarily was writing JavaScript functions and interacting with our contracts from the web console, but rather writing contracts themselves, which attack other contracts. If you've ever seen any kind of flash loan attack or some of the more complex attacks that occur, particularly in DeFi, these are always initiated by other contracts that have been written and that make use of some particular feature of the EVM or the shared environments, or just the way in which these decentralized networks function in order to gain access that they perhaps were not intended to have. And we'll be looking at a lot of these kinds of patterns and a lot of these kind of features, because as I kind of hoped to illustrate last time, the environment in which these things live, love, and operate is radically different to what has come before. Right? People often talk about the development of Web 1, Web 2, Web 3, and there's two things to say about that. The first thing is that the first time Web 3 was mentioned was not in the context of blockchains, smart contracts, and these kinds of things. It was really the semantic web. It was put together by Tim Berners-Lee and some others who were the people that were actually working on this notion of semantic linking, right? Like links that carry meaning, not just these universal resource locations, but links that are inherently themselves linguistically meaningful primitives. And they were the guys who actually worked on Open Graph. So if you ever have been in any way involved with metadata and SEO, and you've written a meta tag into your HTML code that says OG title or OG URL or OG image that is used to display an image or a title when you share a link in Slack or share a link on Facebook or whatever. That's Open Graph, and it was developed by these guys making the semantic web, and then kind of co-opted by Facebook. Twitter. Mark.
Andy, could I add something to that?
Please.
I really would, because I thought about this a lot. I was really deep in this when I was doing decentralized data a few years ago. But exactly what you're saying, one thing that I wanted to add is that this notion of what's called hyperdata in the idea of the whole semantic web, and something that when you're describing about meaning being inferred across the semantic internet, is that we don't have an HTTP for blockchain. And HTTP for blockchain is hyperdata, which is what Tim Berners-Lee and his people have talked about for a long time. Is this the idea of, instead of hypertext where text is linked to other text like we use on the internet, we don't have a data schema for data that connects to other data across blockchains. We don't have a common data schema. We don't have something that, like we use in all our web browsers across all our different systems that connects to the internet of blockchains. We still don't have that in blockchain. I think, there's IPLD, which is IPFS's interplanetary link data, and they've been trying to tackle this problem for a long time, but they haven't really figured it out yet. They've been saying it's going to come every year, and they're like, oh yeah, it's been delayed another year. Oh, it's going to be delayed another year. It's like, oh, I still haven't figured it out yet. So I bring that up to everyone because this is something that I've wanted to see for friggin' years in blockchain, is someone figuring out how to do hyperdata in a Web3 context and blockchain context, because then our wallets won't suck. We can surf the internet of blockchains and applications and experiences without all this switching networks and all this clunkiness that makes the user experience really, really, really bad. Yeah, anyway, I had to say, because I'm really passionate about that piece, because I feel
Nice.
because of that, we still haven't had our Netscape moment in crypto. Like it's just not, we haven't had it yet. So anyway, I really wanted to add that piece.
Thank you so much, truly.
There's two things there, Mark. It's Ben here. In a previous life, I was working on machine as a service, and basically what that means is more and more factories are getting, really expensive equipment that no one can afford. So the factory owner says, okay, you guys are only going to get paid when I start producing widgets, but you need to have 5 or 6 machines working together to do that. And nobody wants to expose their secret sauce or the source of their contracts or whatever. So they're starting to use secure enclaves and blockchain as a distributed trust mechanism so that everybody can say, well, I delivered my piece, so that they can develop a payment mechanism. So that's moving pace. Also within the medical sphere, you're now starting to see medical scanners, which can actually update patients' treatments in real time based on scanning their biometrics and data and so on. And that requires a distributed trust between the patient and the machine and the owner and the hospital and everything else. So you're starting to see these islands of shared trust and distributed trust and confidence scores and all that kind of stuff. But I'd agree with you, it's going to take quite a while, but there's definitely some promising stuff happening there,
Yeah, that's a little different from what I'm talking about, but that is great news. I love hearing those type of stories.
Okay.
If what you're talking about comes true, it's all connected anyway. And I really appreciate the point, because there's something else that what it reminds me of is that a good friend and teacher of mine once sort of said to me that without passion, it's all just boring religiosity anyway. And this kind of reminds me of a particular quote from this week's module, which comes from Simon de la Riviere. So I'll start sharing my screen because Simon is also a crazy South African and a dear friend. And he's talking about this kind of environment. And the reason that I share this is we're going to be looking at what this actually means from the level of smart contracts and writing some of our own in this session. And so it's worth having the kind of background, what both Mark and Ben have so beautifully shared, of this like deeply interconnected, hyper connected realm in which these things operate. And Simon says in our meaning module from this week, which hopefully everybody has read or at least skimmed over, that when you have an environment in which any program knows exactly both the state and processing capability of any other program, it's essentially like inventing religion for machines. This notion of verifiable computing protocols, a program knows the minds of other programs. And there's no longer this idea of servers and data and logic connected disparately through the network. The data and the network is everywhere, right? Which is the point that is made at length in this very beautiful video from Vinay Gupta and the brief which follows, if you want to take a look more and more at what that really means, this notion of servers and data kind of being everywhere. The 2010s section holds a lot of it. So, like that sounds maybe a little bit idealistic and abstract, but it's what we're actually going to explore today by finishing off what we should have finished off last week. And I was rambling along a little bit too much, and then diving into actually writing our own smart contracts. And so just to kind of remind you of where we were and what we're going to be doing, we talked a little bit about MetaMask, the fact that it uses an RPC or remote procedure call to get what it needs to their infrastructure. In this case, it's just a signed transaction blob that has to do with the keys that are generated in your browser. And these keys are like your home address, which you can share either with number 1, Steenbrus Drive, but the private key, which is kept in this extension in your browser, is like your front door key. And that's what's actually used to sign any transaction, just submit it to MetaMask. They put it onto the network, get the result back, inject it into your browser using a little bit of what we talked about when we opened our web console and said, what is going on with this Web3 provider? And that was kind of what's allowed us to interact with our contracts. We didn't take a great and detailed look at exactly what MetaMask is injecting with this Web3 object, but we will today. And we also managed to go through at least the first tutorial, which was this fallback contract. And you'll remember what we did was created a new instance, which allows us to have our own bespoke contract deployed onto Rinkeby that we get to interact with and claim ownership of. And the point of this tutorial was that we had to try and claim ownership of the contract and then reduce its balance to 0. We looked a little bit at the structure of a smart contract, how it declares a compiler version for Solidity, because we know that this code that we can read as human beings is not what actually gets put onto Ethereum. The Ethereum virtual machine consumes hexadecimal data, right? So we have to have some other computer program that takes what we write and can reason about and can understand and compiles it down into a list or a long string of numbers and letters, rather just numbers, and those numbers are what actually kind of live on the blockchain. We also took a little bit of time to consider the fact that Solidity is very similar to JavaScript, but it has this notion of types. So you declare an address or a uint. We don't have those here, but those are unsigned integers, or a mapping, or some bytes, or an enum, or a bool. There are all of these different types of things that can exist in your contract. And we looked at this contract and we said, okay, we can always declare contract objects. We can also import specific functionality that we need, particularly from the wonderful open set and libraries, in this case, to do safe mathematical calculations. An interesting side note for any of you who are developing further is that as of Solidity 0.8.0 and above, safe math has been incorporated into the language itself. So you no longer need to use it here because we're still using 0.6.0, it's included. And we looked at how this contract is put together, right? The constructor is the function that is called once when the contract is deployed. And in this case, it sets the owner of the contract to whoever sent the message that deployed this contract, whoever submitted the transaction. Message.sender, along with a number of other globally available variables, are again something that we will be looking at today in Coinflip. And it also initializes the contributions mapping at the key of the address associated with message sender to the uint, the unsigned integer of 1,000 ether. So it says that's whoever deployed this contract, we set that mapping to 1,000 ether. Doesn't mean that they actually paid 1,000 ether, which is an interesting thing that we can discuss, but it just sets that mapping. And the reason for that in the context of this contract was that, the only way at first glance to become the owner of this contract is to contribute more than the current owner. And yet this contribute function requires that every contribution sent is less than 0.001 ether. So it would take you 1 million contributions of 0.001 ether to become the owner, which we were not willing to do because all of us have better things to do with our time than just repeatedly call some contract on Rinkeby. And so we thought that there needed to be another way to hack this contract and take ownership. And we took a look at what is called the fallback function. You can see that this is delightfully disguised by the Ethernaut team because it is actually seemingly given a name, but because it's not declared as a function, this is whatever, this fallback contains whatever logic will be called if any random transaction is sent to this contract. A random transaction or a transaction that specifies some function method that is not declared by the contracts. They always trigger the fallback. And it's a terrible idea, generally speaking, to have critical logic in your fallback function. Here we can see that we're changing the owner in our fallback function, which was not a good idea. And so the way that we took control of this contract was we sent one contribution in order to get past this particular requirement, which says that the contributions mapping of whoever has sent the message to this fallback function is more than 0. So we did that. And then we sent a transaction without specifying a method that had some small amount of value associated with it to get past this particular requirement, which is that the message value sent to this fallback function is greater than 0. We became the owner. And because we became the owner, we could then withdraw the balance. You can see that there's another little feature of Solidity here, which we didn't talk about too much last time, which is this modifier. Every function in Solidity has a whole bunch of scope variables that you can declare, right? Public is what any function defaults to. There is also private, there is internal, there is pure, there is view, there is payable, and then you can write your own modifiers. And in this case, we've written a modifier here called only owner, and that makes sure, if I can scroll up, that whoever is sending the message is exactly equal to the owner of this contract, which is a public and global variable. If it doesn't, then it uses the shorthand underscore, which you might not be able to see very well, to revert. That's just some syntactical sugar for our modifiers in Solidity, which I'm not a big fan of because it's difficult to read, but whatever. In general, I'm also not a big fan of modifiers because they make it easy. I mean, they make it harder to audit and understand the logic of any given contract. Sometimes they are necessary in terms of having composable and modular code. If you have a contract that requires the same conditions to be checked for multiple different functions, then it's worth having a modifier. But if you're writing a contract and you only use your modifier once, it's probably better to include the logic directly in the function itself, because then it's readable, it's logical, it's much easier to audit, and I don't have to jump around the contract looking for the logic that is actually being executed at any given point. In addition to that, the one other thing that I want to say about this before we dive into the next few contracts is that we spent a lot of time early on in the Ethereum community, particularly running around at hackathons and conferences and all of these kinds of things, pasting signs above the toilet doors and in other places where you couldn't fail but notice them to say, you don't want to be the only owner when the FBI comes knocking at the door. These networks, it's such an interesting thing to think about from a philosophical perspective, that like the whole attraction and narrative of Bitcoin, especially when it got going, and also Ethereum, was that these are ownerless networks. They're accessible to everyone. They're permissionless. Nobody owns them. And here we are writing code that defines ownership. Very ironic. So think carefully about how you strike a balance between access control and actually benefiting from the medium in which we're working and not actively working against it. Right? This is kind of what Naran was talking about yesterday in the fireside, of like community life, that there are ways of thinking about these particular networks and technologies as a reaction against the enclosure movement, which has been operative in modern society for the last 400 years. And because it's been around for so long, it becomes deeply conditioned into how we think about things, such that like writing an only owner modifier is a very common practice. It's not really given much thought by anybody who does it. And that's, to me, strange, right? Funny in the sense of being strange, because we have the potential to use these new languages and new media in which executable language is deployed in a deterministic, shared and public global fashion in order to think deeply about how it is that we define boundaries, how it is that we include or make permeable the ways in which we organize, such that people can come and go as suits them rather than some centralized rule set. The other thing to say about this, because it's a hobby horse of mine, is that, you know, ever since we've been able to write, ever since we've been able to externalize consciousness into some other medium that lasts beyond the scope of a single human life, we have been as time travelers, right? Books are the proof of that. Books are proof that humanity is capable of magic, Carl Sagan says. And another time he says, you know, we are already as time travelers, we might as well get good at it now. And when you read a book from 500 years ago, who's really speaking in your mind? Such a fascinating question, right? Like, is it you? Is it the author? Is it some mix of the two? What is that voice? You know, like what's happening in consciousness when that kind of thing is going on? And now think about the step function change in our ability to cast consciousness across time, right? The states of Bitcoin and the states of Ethereum are going to last orders of magnitude longer than paper or papyrus or even stone and clay tablets that we've had in the past to perform the same function. And when you encode ownership or this limited notion of ownership into your contracts, you make them deeply vulnerable along this dimension of time, right? Because sure, you might have an owner now for this human life, but is your contract really going to function 500 years from now, let alone 100,000 years from now? You know, the dimension of time along which we have to think is radically different. And these kinds of modifiers and this style of thinking is deeply vulnerable to the test of time. So, you know, it's always true that history will judge us. If you deploy a contract onto Ethereum, history is going to judge you very, very precisely. So watch out. Right, Fallout. This is a fun and easy.
I have a question.
Please.
I need source how to owner level contracts, like any keyword only of right. So
Is Sid lagging for anyone else?
Yes, he is.
Sid,
Yes,
your connection's coming in and out.
It's cutting.
Cool. I think that I heard the question, Sid, and I will show you. You can tell that I'm not in my.
yeah, is it better now?
Yes.
Oh yeah, much better.
So I will
Yeah,
show you
so
a
the-
contract that I have written,
Sure.
which adheres to at least some of what I'm talking about here, right? This is a contract which curates information on this website, which is primarily meant for mobile discovery of distributed applications. And if I just switch onto the main net very quickly. So this is the application, and it uses tokens to rank distributed applications in a transparent economic fashion. And if you look at the contract that sits behind it, let's see if I can, Zoom is making this difficult for me. If you look at the contract that sits behind it, you will not find a single modifier or only owner notion you will in this entire contract, right? Which is radically different to any other kind of curation mechanism that currently is in production on Ethereum. This contract achieves Sybil resistance by the use of simple economics and operates according to an extraordinarily simple mechanism, which says that whoever stakes the most tokens ranks highest, with the simple caveat that the more tokens you stake, the cheaper it is for people to downvote you. The way that we achieve that is with a very simple exponential curve, a bonding curve, but it's not a bonding curve in the sense that it's normally meant on Ethereum,
We
because it
talked
doesn't.
about meaning quite a bit throughout in a secular age, but let me ask you the big
Hello?
ridiculous.
Okay, we'll carry on unless that's a question. Was that a question?
No, I think that was Rich watching a video.
Okay. Okay, cool.
I
So
think that Alfreda is raising hand.
Yeah,
Freedom.
I have a question about the ownership in the contract, and because I'm interested in like music ownership, and that you're owning your songs, and that the musicians have their full rights in owning their yeah, the song that they make. And in the context of contracts, and if I'm building this like a record label for musicians, I need some sort of contract that applies ownership for the song. Do you think it's optimal to code that into the contract and like set the owner that way, or is it a better way to do this, you think?
I think that's what I'm pointing at, Elfrida, is that there are more creative ways to think about what I would call stewardship, right? Or guardianship. There's a different language to be used here, right? And it's not just about the semantic word that we choose to use. It points at a deeper understanding of what it really means to, for instance, produce some creative work, right? Because there's nothing new under the sun. You know, the wonderful, if you want to read where that actually comes from, it's Ecclesiastes 3, a stunning book. Ecclesiastes is incredible. It's wonderful. I highly recommend it, even if you're not Christian. It's really funny. But there's the sense that there is nothing new under the sun. There's no such thing truly as an original thought, right? Which is what most great artists will tell you, that the real masterwork is a patchwork. It is so there in that vein of thinking, right? There are ways of encoding the ability to receive due reward, to have royalties flow back through a network of attribution, to ensure that the incentives of any kind of creative endeavor are created such that it rewards the person who sort of propagates the little piece of data that begins the whole thing, right? Like those things are absolutely beautiful, necessary, and very wonderful things to do. And I think that these networks provide like a perfect opportunity to do that. It's just that you're not the owner. That's all that I'm trying to point at, right? Is that like these networks are not about ego. They're not about control. They're not about getting what's due to me, right? These networks are about telling a story that is outside of the scope of a single human life, that does not have to do with what I control or what I create, but about what I contribute, how I participate, how I am a part of something which is larger than me, because that's literalized in a technological sense in these environments, right? Not some mystical kind of woo-woo sense of like, oh my, you know, I'm bigger than something, I'm part of something bigger than me. I'm literally that, because like this is the environment, this is the media environment in which the stuff exists. So I'm not against like reward, I'm not against attribution, I'm not against proper compensation for the work that we do, and for creative ways of valuing what work is actually important, right? I think all of that is critical. I think that the way we do it is precisely by not, you know, falling into the old traps of ownership and control. The example that I always go back to on this particular front is, you know, the only nation, the only indigenous nation that was able to withstand colonization from the British Empire was the Maori in New Zealand, right? Something I know a lot about because I live in an area where the British, fought many wars, not just against the Zulu nation here, but also against the Boers and the Afrikaners. They eventually ended up winning here with some really fascinating historical sides. But the Maori in New Zealand were the only people who reached a treaty agreement with the British Crown. And it's absolutely fascinating to think about because it's called the Treaty of Waitangi, if you're interested. And it's fascinating because a British man and his son translated the entire treaty, which was written in English, into Maori in the course of one night. And they, of course, in doing it in such a rush, made some really critical mistakes. The biggest one of which was translating the Maori word kaitiki, which in Maori means guardian. It means guardianship, right? And the Crown was saying the Crown will be the guardian of New Zealand and her people, right? And in Maori, guardianship was understood as this dynamic relationship with them. You were guardians of the rivers and the trees and the ocean, and that didn't mean that you owned them. It meant that you were responsible to and for them, right? Please, can we keep microphones off, please? Saskia? Okay, thank you very much.
On the note of what you were saying though, Andy, I couldn't agree more, and it's something that most people don't realize, is that nothing of us is really original. We're the combined effort of everyone we've ever known and everything we've ever known all around us. We're just soaking in influence from everything everywhere, and we're remixing it. And what you said about the idea of a musician or a creator creating something, I mean, they're really just taking influence and things from everything around them that has already existed that they didn't create, and synthesize it in a way that is perhaps unique to themselves and unique in some way or fashion. And something that I would love to see someone in music do this, and you said it as well, which is I love you, is that you should incentivize people to remix and steal your ideas and make it easier, and then have a piece of even those derivative works, and you make it easy for people to, because good artists copy, great artists steal, and Apple is a notorious stealer of great technologies to build what they've built, and musicians should incentivize that type of behavior as well. I think we could see some really interesting experiments exactly on your note. I've been telling friends that also, so I love where your brain's at. You're awesome.
yeah. So Alfreda, the other example of this, just because we're on it, and another hobby horse of mine, apart from Waitangi, and this really beautiful Maori word of kaitiki, guardianship, and what that means in terms of responsibility and care, not ownership and control, is the great insight at the heart of the life of Mahatma Gandhi, right, was that if you take the primary means by which your culture and society exerts control, in this particular case, it was imprisonment, right, which in Eastern philosophy in general is the single most inhumane thing that you can do, right? To imprison another human being is considered the single worst karmic action that one can take, right? And yet this is precisely what was going on in India at the time. And Gandhi's great insights, and what sits at the heart of Satyagraha, this non-violent movement that he was the father of, was, if I make that thing which is completely detestable and which sits at the heart of the power of the system in which I exist, if I make it desirable, I break the whole system. So he made being imprisoned desirable. It was suddenly this noble thing to go to jail and to hunger fast and to put yourself on the front line for your cause. And then all of a sudden, everybody wants to go to prison, and the whole system collapses. Amazing, So it's the same insights that exists at the heart of what Mark is saying, right? Which is that we're constantly borrowing, stealing, syncreting. Yes, we create unique things, but if we have this environment in which that kind of give and take exchange is actually at the heart of how value is created, described, and transferred, then all of a sudden, remixing and borrowing, stealing, giving back, it becomes this really beautiful cultural action, not something that happens in the shadows. It's an incredible thing. The reason I mentioned Gandhi is because a lot of what became Satyagraha and this insight of his about going to prison was because he was actually imprisoned in a prison here in South Africa, the same prison as Nelson Mandela, where they met. And that prison in Johannesburg is now our constitutional court. It was turned into the constitutional court after 1994. It's the most incredible place to go and visit. It's just haunting in so many ways. That this prison, which was the heart of apartheid power, where we declared in law that we are separate, was the place where Gandhi and Mandela spent time together, and out of which grew one of the most progressive human documents ever written. It's amazing. So yeah, anyway, that's taken us a long way from Solidity, which I want to get back to. But thank you very much for the question, and it's a wonderful question. And I'm not presenting like the answer. I'm just saying that, like, if we think about ownership in a creative sense, if you think about ownership as another kind of song that you're writing, where does it land you? Like, where can we go if we just notice these ideological traces that come along with our culture that are not necessarily serving us anymore? So, fallout. This contract, as you can see, is very similar to the first one that we wanted to do, and we need to claim ownership. So it seems very similar to the fallback one. And if you look at the structure of the contract, we have exactly the same sort of variables declared. It's not called contributions this time, but allocations. But we're using safe math. We've got this mapping from address keys to unsigned integer values, and we have an owner, which is an address. Then we have this constructor, which sets the owner to the message sender and allocations of that owner to the value that was sent when the contract was created. We have the same only owner modifier, the same sort of allocations. It's not quite the same. It doesn't have that require statements, but it says the allocations mapping for whoever sends us a message will get updated and will add to it whatever the value of that message is. Okay, so that's fairly straightforward. We have this send allocation, and we have to pass in an address. It's a public function. We require that the allocations mapper for whoever we're sending this to is more than 0, and then we transfer it to them. Okay. We have collect allocations. Only the owner can call this. And if that passes and it is the owner that's called it, then we transfer to whoever sent the message the entire balance associated with this contract. The address of this means, this contract, it's referring to itself. And then one last function just to get the allocated balance, which returns the allocations for whatever address you sent it. So there's no obvious way, to kind of claim ownership of this at first glance, right? Like, we don't have the same fallback function, which had the logic to change ownership from the previous thing. There's no funky logic going on in any of these functions. So what is it that we can do to kind of overcome this? And when we really kind of read it and look at it, there's something kind of strange going on here, right? It's called a constructor in the comments, but it's not actually declared as that, right? That's kind of weird. This is not a constructor, it's just a normal function. And oh my God, if I actually kind of read that, it's FAL1 OUT. So that's sort of interesting, right? This is a artifact of how Solidity worked earlier on in its lifetime, which was that if you had a function that was named the same as the contract, so this contract is called fallouts and this function is called fallouts, or at least seems to be, then that function would be the constructor. It's no longer the case these days, precisely because people started doing this kind of stuff. You have to declare the constructor explicitly, like you see it's declared here. Right? You have to declare it as a constructor. But back in the day, you didn't have to do that. It would just, if you had a function of the same name as the contract, it would be assumed to be the constructor. But this is not, this is a normal function. And all it does is it assigns the owner to the message sender, and it updates the allocations mapping with whatever value you pass in the message. You don't even have to pass any value, it just does that. So it's really easy. We just have to call this function and we'll become the owner. Before we do that, the one thing that I wanted to mention was comments in Solidity are really critical, because when you're writing legitimate contracts, it helps people understand what you're thinking, how you're thinking about it, and why you've written stuff in a particular kind of way. And there is a standard for comments in Solidity, which is called NatSpec, which is the natural language specification. So you can find it in the Solidity Lang docs, which are really comprehensive, and I highly recommend them. They're well-maintained, well-written, clear, lots of examples. And here you can see both the sort of genesis of NatSpec, which was another standard called Doxygen. And NatSpec is really, really useful in Solidity, not just because it comments your code and helps other people who are developing with you or auditing your contracts to understand why things are the way that they are. The comments can actually also be passed up to the user. These messages can be shown to the end user at the time that they will interact with the contract. If you use NatSpec, because that functionality has to be implemented by the wallets, and they require some standard to write code against. And so NatSpec has been the one that has emerged. It was begun by Louis and Jorge at Aragon, big love to those guys, and has become an industry standard. If you go and take a look, you can see that there are different ways of declaring comments in Solidity and Viper, and there's some sort of really wonderful examples of what comments actually look like. Generally speaking, for like any function, you will have like a dev note about what the function is and why, what parameters you're passing to it, if it returns anything, and maybe like some kind of notice to be shown to the user. There are any number of tags that you can actually use, not just notice, author, dev, param, and return, but also a nice one called inherit doc, which I don't see used that often, but it's kind of fun, and some custom tag to do custom things in your contract. You can see that there's one here for the note that this is kind of an experimental contract, clearly, because it's in the documents here. So there's all sorts of really fun things that you can do. And I highly recommend these docs. I'll point to them another time, slightly later in what we're talking about today. But we've been able to identify that this is not actually a constructor. It's not commented in the right way, and it's sort of a very, very misleading comments, which also helps me touch on one of the questions that was asked after our session last week, which is that, like, if I have a verified contract on Etherscan, can I automatically trust it? Like, no, you can't. Just because it's verified doesn't mean that it's is not still shady in some regard. And this is like a good example of the kinds of things that can go on, that, like, even if you have a verified contract, there can still be some kind of like backhanded activity around using characters that look the same or having misleading comments, this kind of stuff. So, similar to what we did last week, all we need to do is call this particular function on the contract. So we kind of get our contract objects, and we're going to call fallout, which I think should be FAO1 OUT. You can see that there's no parameters that need to be passed to this. So that should be enough. Oh, so sorry, you need to actually get your own instance first. I'm getting a step ahead of myself. I was wondering why it wasn't picking up that object. But if you get your own instance, deploy a contract that we can actually attack before being an eager beaver like me, then you should be able to call this simple function claim ownership, and we can move on. Let's try that again. Can everybody still hear me?
Yes.
Yes, we can, yeah.
Yep.
So there's the actual function that I want to call, the one with the one. And if I do so, because I'm changing the state, we're updating the owner, which is in storage of this contract, and therefore updating state on the network. It's going to be a transaction for which I have to pay gas. And hopefully that will go through soon on Rinkeby, and
So
we will.
So what's a good description of the await function? Like, how do we think about using await?
Await is just a particular helper in JavaScript, right? That's we're interacting, like the Web3 object that is being injected by MetaMask and the code that we're using in this console here. This is a JavaScript console, right? Because JavaScript is kind of what rules the web. And await has nothing to do with Solidity. It's got to do with JavaScript, and JavaScript is running these asynchronous functions, right? Because what's happening is we're saying, call this contract and call this function on this contract. And then we have to, like that information gets passed to MetaMask, which gets us to sign it and submits it onto Ethereum. Then Ethereum returns its response, and MetaMask returns that to us, it's Web3 providers. So like, it's asynchronous, right? It doesn't all run at the same time. There is this period in between it. And lots of code in JavaScript is asynchronous, not just blockchain stuff, although blockchain is highly asynchronous, as we all know. And so the await thing is just telling us, rather than let's show you, if you just called contracts, Fallout, then you'll see like it returns a promise immediately, right? So forgive the red stack traces here, but it's returning this promise immediately. It says like, okay, I'm going to take what you've asked me to do. I'm going to go and do that stuff. And like, here is my promise that I will get back to you as soon as all of the things have happened. And when we use await, it just like, it receives that promise and it says, okay, cool. Like, I'll just wait here until you like get the information that I'm actually looking for back to me. And only when that happens, then I'll display that. So that's, it's just easier to read and navigate. Yeah.
Thank you.
Sure. So we can check if we want to before sort of submitting our instance. And as always, we can call the contract.owner to see who our owner is on this contract. It's 0x5f33, which is my address. Wonderful. I was right about the constructor. Surprise, surprise. And if we submit the instance, we should be able to move swiftly along. Swiftly, depending on Rinkeby. I keep on forgetting to get some elevator music while we're waiting for these transactions. There's some really wonderful stuff that's been posted in the kernel jam music channel if you're looking for that. Yeah, you can find for yourselves and listen to Moby, one of the others that has been posted in there recently. The nice thing about what Ethernaut does is when you pass the level, not only does it put all of this colorful, delightfully happy stuff into your console, it also gives you an example of when this kind of thing was actually seen in the wild. And the story of Rabixi is what happened and what led to this particular tutorial, right? And that's something interesting, which I actually haven't mentioned now, and I haven't given full due to the Ethernaut team for this, is that every single one of these tutorials is replication of some kind of hack that really happened on Ethereum. So this is not just like the imaginings of some random developers, mostly from Argentina, those delightful people, but it is a replication of things that we've really seen in the wild. And so if you want to kind of read about the stories associated with each one of these hacks, then it's what appears after you pass each level. So yeah, they changed their name and they didn't change the constructor in their contract. It's kind of funny to think about. Anyway, before we go into Coinflip and telephone, I want to do token, which is number 5, because it doesn't require us to go into remix, which we will do in the next hour. And this one is also like fairly easy from a actual code perspective, but from an understanding perspective, we are going to have a little bit of fun with this too. And so if we look at the description of this level, it says the goal is for you to hack the basic token contracts. We're given 20 tokens to start with, and we'll beat the level if we somehow manage to get our hands on any additional tokens, preferably a very large amount of tokens. Okay, so let's have a look at this token contract. Again, we have our license identifier, MIT. It's a great license, share alike. We spoke a little bit about it last week. We have the same declaration of the 0.6.0 or above Solidity compiler, or above because it has that caret there. Generally speaking, if you're writing your own smart contracts, this is not best practice because it doesn't, you're not being specific about what version of Solidity's compiler you're actually using. And you'll see that most sort of contracts in production actually specify a much tighter range of compilers. It's still kind of easy enough to develop with, but making sure, for instance, in this case, that anything greater than or equal to 0.8.2, but less than 0.9, i.e. less than the next major version. When we change this number from 8 to 9, we change the major versions, and there, when we change major versions, there can be breaking changes. When we change minor versions, generally speaking, no breaking changes. That's kind of wider software best development practices. And when you're writing contracts, generally specify a tighter range when you're getting closer to production. But this caret, it says anything above 0.6.0 is kind of useful when you're writing your own smart contracts, because like your framework and whatever environment you're working in, it makes it easier, because if you specify exactly what compiler version you have and it's different in the framework that you're using to write the rest of your code, then you can get strange errors, and developers don't like that kind of thing. So that's what's going on there. Anyway, here's the very simple token contracts. It has one mapping, which takes addresses and maps them to unsigned integers of the balances associated with those addresses. And it has an unsigned integer, which is public, of the total supply of the tokens. Then when it is constructed, when it's deployed and this function is run, you pass the initial supply in as a parameter. It sets the balances mapping of whoever sends the message that deploys the contract to be the total supply minus whatever initial supply, total supply, which is also equal to the initial supply that you created it with. And then it has two very simple functions, right? The first is transfer. And here we give it an address that we want to send it to and some integer of how much we want to send to that address. It returns a Boolean, which is true or false. Boolean logic is always true or false, named after George Boole, incredible English mathematician, fascinating historical study, big fan. And if we look at the logic of this transfer function, the first thing that it has is this check, right? This require statement, which says that we require that the balances mapping of whoever sends this message to transfer tokens minus the value that they send is greater than or equal to 0. Right? So you first read that, you're like, okay, cool. Like it's just saying that my balance less whatever value I'm trying to send must be greater than 0. Otherwise, I can't send it, right? I can't send 100 tokens if I only have 50. That seems to check out. And then if that check passes, then we have like the balances mapping of me, the person sending the message, is minus equal. So this is just fairly common kind of programming language that says that like it minus the value that I'm sending from my own balance, right? Like my balance is equal to something at the moment, minus subtract that value that I'm sending away from it and add that same value to the balances mapping associated with whoever I'm trying to send it to. And if all of that is successful, then you can return true. And then there's just a balance of function, which again is public view only. So this view, I mentioned that there are these scope variables. View and pure both mean that it doesn't change state. It's just returning some information. Whereas like this, for instance, here, these are two state changing lines, right? They're changing this balances mapping in our contract, which is in storage. And the storage of every contract is bundled up into the overall state of Ethereum. So that's why this is not a view function, but this one is, because it's just looking into the balances mapping of whoever we're interested in and returning the balance associated with them. Okay, so we know that if we get our new instance first up, wonderful. We know that apparently we have some tokens, which once the contract deploys, we can maybe take a look at. So if we look at our contract object and call balance of, and remember that our address is stored in the player variable by Etherscan, then it returns this rather nasty looking array, but we can see that our balance there is 20. Right. There are better ways of like displaying this, but unfortunately, recently MetaMask removed the big number library from the Web3 provider that they inject into web pages, and so this is kind of the best that we can do for now. I don't really want to go too deeply into it, but like numbers are stored as these hexadecimal integers on chain, and so converting back into like human readable stuff in JavaScript has traditionally been like a little bit of a mission, but there's this wonderful library called Big Number that used to be able to sort of pass this object that's being returned here, but that's no longer the case. So we just sort of need to look into it, and we can see that we have a balance of 20, which is good enough. So how are we going to get more tokens? It's really there's really only kind of one line that is any kind of check. It's got to be something to do with this line. And it's a subtle but really fascinating aspect of programming, which I hope to use to illustrate some deeper aspects of the universe, because that's what I'm really wanting to do on Fridays, which is that when we try and send some greater value than the balance associated with our account, our address, it doesn't behave like you would ordinarily expect. Right? You can see one of the major differences between this contract and what we were looking at in Fallout and Fallback is that it doesn't import safe math, right? And it may have been difficult for you to understand, why the hell would you have a library for safe mathematical operations? Surely just like minus and plus and divide and multiply are like, they're very straightforward things. Like, how on earth could that not work in Solidity? Why would you need to have a library to do that kind of stuff? Well, it's because there is this wonderful thing called integer overflow. And in order to understand it, we need to understand just a little bit about binary. So for instance, we're dealing here with like uint total supply, right? But Alon, perhaps you could mute. When we declare a uint, it's assumed to be uint 256. But for the sake of this demonstration, if we had a uint 8, right, which means there are 8 bits that we can put in it, which was 1, 2, 3, 4, 5, 6, 7, 8. right? This would be, Alon, could you maybe mute?
Oh, sorry guys. Sorry for this.
No problem. This particular 8-bit integer is, does anybody offhand know what this is in decimal representation?
255.
Thank you very much. Ben, was that you? Incredible.
Yeah, afraid so.
The experience kicking in, it's incredible. Well, yeah, really amazing stuff. And the way that we get to that is we say that, you know, the left bit here is the most significant bit, and that's 2 to the 8, right? And because it's a 1, we have 2 to the 8. And then it's plus 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 1, 2 to the 0, minus 1. So this would give you 256 minus 1, which is 255, as Ben says. Now, if we added 1 to that, right, in binary representation, what happens? And the fascinating thing is that this kind of, it reverts all the way back. It doesn't get bigger. It doesn't go to 256. You can't store that in a uint8 type in computer science. This resets back to 0. And because Solidity is operating along similar principles, right, not entirely the same, when we have a balance of 20, for instance, in this situation, and we try and subtract, say, for instance, we call this function with the value 21. 20 minus 21 in Solidity is not minus 1. It's some horribly large number, right? Because it overflows. The field is not expecting that. So that's what the safe math library is actually doing. It's protecting against integer underflows and overflows. And when you don't use it with a compiler version less than 0.8.0, and you just use the sort of out-of-the-box mathematical operators, you expose yourself to this kind of very strange behavior. And the one thing that I kind of wanted to say about it, because it just really excites me enormously, is that it's actually not very strange behavior at all, because this actually points at a very deep and beautiful mathematical truth about our reality, which is that numbers wrap around, right? It's not even binary numbers, but decimals too. And if you've ever heard of the Ramanujan summation, you will know what I'm talking about, because the sum of all positive integers from 0 to infinity is actually equal to negative 1/12. It's one of the most surprising results in mathematics. If you would like to learn more about it, I will post both this link and a particularly beautiful link about the Riemann Zeta function and analytic continuation into the channel. It's absolutely stunning. But when you think about it, it's really just such a mind-bending idea to consider, right? That 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way to positive infinity, loops around on itself and ends back at minus a 12th. It's really fascinating. It points at the potentially torus-like holographic nature of the universe. That is all I will say about it. I strongly encourage you to become a little bit more familiar with the Riemann Zeta function as well. The reason that I've put it there is because it relates to this Ramanujan summation, but it also relates to prime numbers. And prime numbers sit at the very basis of how we do most cryptography. And so it's really kind of interesting that a deeper understanding of the zeros of the Riemann Zeta function are always prime numbers. And you know, that is baked into a lot of cryptography and sits at the heart of some of the things that we just briefly touched on yesterday in terms of elliptic curve manipulation and the kinds of scalar multiplication and stuff that are going on there. They're all connected. It's really wonderful. But just so that I can stop nerding out.
Could you share that in the chat before you forget the video?
Yes. I did.
Yeah, I'd love to check that out.
There was some, as you can imagine, there was some controversy when Numberphile did a video on it sort of initially, and then Mathologer, who's this really German wonderful, very precise German engineer sort of called them out for doing like an incredibly simplistic proof, which was actually wrong for this Ramanujan summation. And then they came back and did that other video as a response. There's all sorts of controversy in the maths world, but it's a whole different story.
Yeah,
Anyway,
I often wonder if the retorts from some other mathematicians in the space, or just in general, or from people that are maybe less aware or like spiritually inclined to believing in these kind of things, so they're defaulting to like finding the thing that's wrong about something, though it may not even be correct. You know what I mean? Like you have to be careful who the messenger is, right? And like the messenger's preconceived beliefs of things in order to like listen to, figure out who's right or who's wrong, I mean, that's how I look at some of this stuff.
Yeah, this particular one, he'll like the mathology one because he's not sort of debunking the underlying idea, which he finds to be beautiful and really meaningful, but the sort of simplistic proof for the masses that the number file crew did, which is they're arguing about method, but they're both like just sitting there looking at this result being like, this is the most astonishing thing in the world. And it truly is. Ramanujan, he was the Indian mathematician invited to Cambridge, who it is said that every single positive integer was a friend of his. And his favorite number was 1729 because of various different properties to do with its cube and other things closely related to that. And it's what Balaji used as inspiration for 1729.com. Anyway, it's a deep rabbit hole that I don't want to go further down. What I want to do here is get myself a whole bunch of tokens so that I can beat this token contract by making it overflow. And it's fairly simple because I can just do it from my web console again. If I call the contract transfer function and pass it this JSON, not JSON, I need to pass it an address and some value, right? So I think that what I'll do is just pass it my instance address. Which needs to be a string. And then the number 21, right? Which is more than my balance. And that should kind of do the trick, I think. So if I sign this transaction, tell the contract, okay, transfer to yourself 21 tokens from me, who only owns 20. Let's see what happens. Hopefully we'll be successful. It's been mined, okay. And as per usual, we've got this transaction object with the hash and logs, which any event would sort of be in, and the receipts, which we can kind of take a look at, which has all sorts of interesting information about what went down. It did seem to pass. So if we just run again, let's see what the contract returns. And we can see, holy crap, there's something very different. Like the last time that we called balance, we just had an array of length 2, and it was 20. So now we've got an array of length 11, very promising. And oh my God, it's just, that's a lot of tokens. Wonderful. So it seems that my sneaky little overflow trick has worked, and I have an incredible amount of tokens in this contract storage. So
that didn't happen for me. Did you use your own Wrinkleby your own account address when you inputted the?
I used the
function?
Instance address. I used the instance address. That's what you need to use here. Yeah.
I see. Okay, I see it. Thank you.
So if you grab your instance address after you deployed it, then pass it in as the first parameter, which is the address 2. Then you should be good.
Thank you.
Sure.
I missed that
Hey,
piece.
Andy.
Yep.
Could you have passed in a negative value as well?
I don't think so. I haven't tried that in this particular tutorial. So I mean, like, you can and see what happens, but it should if you passed in a negative value, my sense of it would be that it would like negative and negative is a positive, right? So I don't think that you would cause the same overflow, which is what we're trying to do here. Yeah, I don't know. Try it, Simon. let me know what happens. I'd be interested.
Sounds good. Yeah, I've been doing the coin flip.
Okay. You can see that it is about overflows. They have to be checked for with these control statements, which is what the safe math library was all about. It sort of automatically does that. And then instead of using plus, minus, divide, and multiply, you have add, or dot sub, or dot mul, or dot div. And that will protect you from doing these kinds of things. Although if you use newer versions of Solidity from 0.8 nowadays, you should be safe anyway. So with that, we go to Coinflip, which is the first tutorial that we'll be writing our own contract for. And it sort of goes to this notion of complementary opposites, which is so big a part of the kernel syllabus, right? That in order to have truly safe, useful, and wonderful, sort of collaborative code, you need to be able to protect against all of the different ways in which it can be attacked. And those ways are not just people finding silly little gotchas in the way that you've implemented your mathematical logic, or being caught out by using function names that look similar to other function names but actually aren't the same, or by some kind of error in using fallback functions or deeper features of Solidity. It's primarily about protecting your contracts from other contracts. This notion of religion for machines that we touched on, religion is a mess. So you have to be balanced about the way in which you interpret such a statement, right? Because knowing exactly the state and processing capability of another program is an incredibly powerful thing, and it's a neutral kind of power, right? It depends on how we use it that defines the outcomes that it inevitably will have. And in this environment, one has to be deeply aware not just of like externally owned accounts and people, but the kinds of contracts and the ways in which they can manipulate your own work. This is primarily of interest to anybody kind of working with tokens or any kind of financial thing. A lot of the work that we've been doing recently on some of the learning curve contracts for kernel is making sure that they're flash loans safe, because that's something that you have to think about when you have tokens. That's people can borrow enormous sums of money and use those to trigger functions and logic in your contracts that might not have been written considering millions and millions and millions of dollars of any given thing. And for instance, when you're using some kind of, in our case, mathematical curve, it's really important that you implement it accurately, because even if you're like one token off per $1 million, if somebody can borrow 100 million in one transaction and do that repeatedly, you're in trouble, right? And so these kinds of things and the open and adversarial nature of the public blockchain is an incredible media environment in which to learn very deeply about what Vitalik calls the language of defense. It's deeply baked into cypherpunk ideology and spirit that there is this notion of defender's advantage in the cryptography that we use, right? It's like you can build a seastead, and at a cost far less than actually building the seastead, the nation state can destroy it. You can generate a key pair by downloading MetaMask for free and clicking create. And it takes nation state level actors and an incredible amount of coordination and power in order to even come close to breaking that key pair. This is what we mean by defender's advantage. But there is another level to this, which is that in open source adversarial environments, when everybody is actively kind of looking at each other's code and trying to see the shortcomings in it, we inevitably and in much shorter iterations and cycles come to the truly secure and resilient, long-term stable ways of patterning our language. And it's really fascinating. And that's really what Ethernaut is all about, right? Like all of these things come from actual hacks. And these hacks are not swept away under the carpet as if they didn't happen. They're tutorials, right? I mean, just think about the paradigmatic shift that is for a moment. We're not saying, you know, I mean, like, don't look over here. HSBC is not committing humanitarian rights abuses by the degree of corruption that is inherent in our institution. We're saying, yeah, look, these are all of the ways that we got hacked. Let's learn from them so that it doesn't happen again. Really wonderful. And it's this kind of stuff which sort of makes me excited about working in these environments. So Coinflip is a very basic contract that is literally doing what the name suggests. It's flipping a coin. And the idea is that we have to guess what the result of the coin flip is going to be 10 times in a row. We have to get it right. And if you're a probability nerd, you'll know that the possibility of doing that is 0.5 to the power of 10. The probability of doing that is 0.5 to the power of 10. Very, very, very small probability that you will, if your friend comes up to you with a coin and says heads or tails, and then flips it 10 times in a row, it's very, very, very unlikely that you will get it right all 10 times. And yet there must be some way to do it because it's here in Ethernauts. And that's probably got to do with something about the medium that we're working in. So if we look at our contracts, we've declared our usual version of Solidity. We are using safe math again. So that's a route that we've shut down. And let's look at the sort of public declarations. We have some uint, which is public for storing the consecutive wins. That checks out. There's something here called last hash, which it's not public, it's some private variable. We'll see what that is in a moment, I suppose. And then this factor, which is, oh my goodness me, just a really, really big number. Okay, so that's cool. We've got some factor there, which is clearly going to have some influence in these coin flips. It seems pretty random. If anybody wants to go and check, this is actually 2 to the 255, but it's just a curious little side note. Then we have our constructor function, which is just setting the consecutive wins for anybody to 0. That checks out. And then only one function here, which is the flip. Okay, and we pass it some Boolean, which is the guess, either true or false. So heads or tails, true or false, same thing. And it is going to return a Boolean as well. So a bit strange. Pass it a Boolean, it returns a Boolean, but cool. And then we begin and we say, okay, we're going to declare some 256 bit unsigned integer called block value. And that is going to be defined by the block.number less 1, okay? Which is a block.number is a globally available variable. We've been looking a little bit at message.sender and message.value, and I'll show you all of the variables now. And sub is just from the Ethernauts, from the Open Zeppelin safe math library. So it's sub less 1, minus 1. It's the block number before its block hash, which is also a globally available variable. And the block hash is a bytes 32 object, which, just like you have uints, you have bytes, and you have strings, you have enums. It's another type that exists. exists in Solidity of type 32. Let's ask Brave to behave. And we're casting that bytes 32 block hash of the previous block number to a uint 256, which is going to be some number roughly, some number as long as the factor, clearly, but also different from it. Then the next piece of logic here says if the last hash is equal to the block value, then revert. So what is actually going on with this piece of logic is this is what last hash is actually being used for. I'm like, okay, cool. It's checking that I can't call this flip function 10 times in the same block, right? Because if this check is if we pass this check, then it sets the last hash to the current block value. So if you've had one successful flip transaction in a block, you can't have another one in that same block because the last hash will be set equal to the block value and it will revert. So it's just closing down one avenue of attack. I know, okay, cool, I can't call this thing 10 times in the same block. Kind of annoying, but that's what that check is doing. And then here is where the coin flip actually happens in this line. It's saying, okay, we're going to have some unsigned 256-bit integer called Coinflip, and it's going to be equal to the block value divided by the factor, right? This really ridiculously big number. Okay, cool. And then it says the side that it turns up on is equal to that Coinflip uint, which if the Coinflip equals 1, then the side will be true. And if not, if the coin flip does not equal 1, then the side will be false. Right? This is kind of like, there's a lot going on in these two lines. Let's just say that, right? And what you need to be aware of is actually rather simple, which is that in Solidity, if you have 3 divided by 4, it equals 0. And so Solidity always rounds down to the next significant number. So if your block hash is less than the factor, it's going to be, then coin flip will be 0. And if it's more than the factor, coin flip will be 1. It can't be significantly more than the factor because they are both 256-bit integers, right? It can only be like slightly more, and in fact, what it turns out is that like it's only the leftmost bit which is important here, and the leftmost bit of the block hash is a supposedly random thing. You know, you don't know what the next block hash is going to be. So if the most important bits of the block hash is bigger than the factor, it will be, the coin flip will be 1. If it's smaller than the factor, it will be 0, and that's how we decide on whether the side is true or false. And if the side is the same as what you guessed when you called the flip function, then we increase the consecutive wins variable and we return true. And if it's not, and you guessed wrong, then we set your consecutive wins back to 0. It returns false. So this all kind of seems to check out. I'm like, okay, cool. I mean, like that seems legit, and like it seems pretty random. You know, I mean, like this number is really big, and we can't know the block hash, can we? Oh, this is a globally available variable, isn't it? That's kind of interesting. So we have looked at NatSpec. Zoom keeps on covering my. I'm gonna have to just do that for a moment. Thank you very much. Here are all of the globally available variables in Solidity. Globally available, meaning that they're wherever you are, whoever you are, contract, accounts, fridge, dog, whatever, you always have access to these variables and they're always the same. The block hash, the block number, there's a base fee, there's a chain ID to tell you whether you're on mainnet or Rinkeby or Robston or Polygon or Coven or whatever. The current block's miners address, Coinbase, difficulty gas limit number, timestamp. message.data.sender.sig.value we've all kind of looked at. Transaction.gas price and .origin is something that we will look at. I think in the next one, if we get to telephone today, which is kind of seeming a bit.
Andy, just a really quick question there. The blockchain ID is a uint. Is that an 8-bit?
No, uints always are 256 unless otherwise stated.
Okay.
Yeah.
Otherwise, yeah, you're down to 255 chains. So.
Yeah.
Okay.
Yeah, exactly. So unless otherwise stated, if it's just uint, it's always uint 256. But if you are a good developer and you're being storage efficient, perhaps you'll use 816 or 32. It depends, and that also depends on like a better understanding of slots, which we'll get to when we do delegation, probably. Slots and storage in how contractual storage is actually constructed. But yeah, so we've got all of these globally available variables, which I keep on moving away from, and everybody has access to these all of the time. So that kind of is the clue here, right? There's no clear way. I'm definitely not going to be able to write some JavaScript in my web console to beat this, but I have access to the same block hash. And that's kind of interesting, right? Because conceptually, what I want to do here, if I want to guess what flip is in each block, is I want to write a contract that can interact with this contract here and has the same logic for calculating a flip. It will calculate its flip when I call it, calculate what it's going to be in that block, and then call this contract with the correct Boolean, true or false. Right? And because that can all happen in a single transaction, I can be sure that like if I call my contract, which has the same logic and calculates the outcome of this flip, that it will call this contract that I'm trying to attack with the correct variable every single time, with the correct Boolean every single time. So in order to do that, we're going to have to open a new aspect of our guild, which is at remix.ethereum.org. And Remix is what we call an integrated developer environment, an IDE. It will look, if you've seen a text editor, it looks kind of similar to a text editor. It has an integrated terminal down here. It has a file explorer with all of the different things that we can do and write. And if you're opening it for the first time, it should take you on a little exploration of your file explorer, of your compiler, of your deploy and run transactions tab. And there are a few other things which one day we will get to in terms of debugging, this sort of stuff. The one thing that I kind of wanted to draw your attention to before we dive into actually writing our own contracts here is a very little known part of like Remix and Ethereum in general, which I think is delightful, is this LearnEth plugin. There are some genuinely incredible tutorials in this LearnEth plugin, and you can see I'm actually doing it at the moment myself in my own capacity, learning about debugging Solidity calls, learning about stepping through the opcodes on the EVM, which is like totally fascinating, very low level and kind of like specific, but it's really fascinating to be able to do. And they have the most incredible tutorials just available here for free in Remix. You don't need to go anywhere else to any kind of other fancy tutorials or pay for anything. It's just there in this incredible IDE. And you know, Remix has been around since kind of the beginning of Ethereum. It's come an incredibly long way. And to the people who work on this in development, I really love you guys so much. It's really, the work that has gone into this over the last 6 years is truly remarkable. And what Remix at a very high level allows us to do is to write our own smart contracts in the browser, to test them, to deploy them onto any network that we like, and to interact with those, all just from the convenience of our own browser. We don't have to download software. We don't have to do anything fancy. We can just get going with our own contracts, test them, deploy them, debug them, and put them where we like. And honestly, I mean, debugging Solidity contracts 5 years ago was just one of the most painful things that you could possibly do. And the work that has happened since then is really just incredible. So we know that we're kind of going to want to attack this instance, and that we're going to want to have the same logic, but just with a few little tweaks so that we can call Coinflip correctly. So if you get your new instance, and while that's happening, I will take a look around our workspace here. You can see that the default workspace comes with sort of 3 contracts. There's my instance address has come through, wonderful. The default workspace comes with these 3 contracts, a few little scripts, either deploying with Web3 or with Ethers, which is an alternative JavaScript library that I really liked, and that is developed by a wonderful, wonderful man called Rick Moo. Has a great Gitcoin grant. I strongly recommend it. And then there's some tests that I can write both in Solidity, which are rare to see these days, but tests in Solidity are wonderful. And you won't have this learn ETH folder, but the other sort of README text is what we're looking at here. So I'm a fan of these contracts, but I'm not interested in them for now. I'm just going to get them out of the way, and I'm going to create a new file, which is going to be my attack contract, and I'm going to call it attack coinflip.sol. And there we go. So this is the first smart contract that we're going to write ourselves, which is very exciting. While we're developing things, we don't need that SPDX license identifier, but because I'm a big fan of sort of doing things fully, I'm going to grab those 2 from the instance that we're trying to attack. I'm just going to set it to 0.8.0, my version of Solidity. And now I know conceptually what we want to do, right? We want to use the same logic that is appearing in that Coinflip contract to calculate what it's going to return, and then send the right answer to the actual contract every single time. And in order to do that, not only do I need the same logic, I need to understand one other concept, which is this thing called interfaces. Interfaces are what allow contracts to speak to one another, right? We touched on them briefly last time when we sort of looked at the contract object itself, right? And we said that one of the most interesting things to look at was the ABI, which is, here we go. This is the ABI, the application binary interface, which that interface is what's providing information about all of the different publicly available variables and the functions that are in this contract. So if I want to interact with this contract from another contract, I have to write an interface for it, right? And that's fairly straightforward in Solidity. We declare that we're writing an interface, and there is a convention that we begin interface contracts, interface declarations with I. So we're writing an interface for the Coinflip contract, right? And the only thing that we're kind of interested in writing this interface is the function that we're going to be attacking, which in this case is flip, right? And this is the function declaration, right? So we can just copy that directly from the contract that we're attacking and put it in, because this is our, the interface declares what functions we're interested in calling on the contract that we're going to be interacting with, and make sure to include a semicolon after that, because that's just required by the syntax. So we've declared our interface, and in our interface, we've declared the function that we're interested in calling. And now we can write our contract, which we declare with a contract statements. And I'm going to call it attack Coinflip. That's what our contract is going to be. And use curly brackets. I wonder, I can probably just increase the size here so that see it better. This it's going to require just a very few things, right? The first thing that we're going to need to do is tell our attack contract where this interface actually lives, what address we're actually going to be attacking, because there can be many different instances of this Coinflip contract, right? And we're interested in attacking the one that's that we need to prove to Ethernauts we guessed right 10 times on. So the first thing that we're going to do is declare an address for our, what should we call it, Coinflip address. And we're going to set it equal to our instance address. And don't worry, I will send a gist of what we put together here, right? Because we can do that into the chat once I've finished writing it. You'll need to change this particular address and some other things, but like I want to sort of demonstrate some of the really cool features of Remix by doing this. So if you like are struggling to keep up with like the code and this kind of stuff, don't stress. I will share the code once I've finished writing it and explaining what I'm doing, and you'll be able to use it yourself to claim that you beat Coinflip. So the first thing, as I say, is I'm declaring where my Coinflip instance is, and then I want to say that there's this interface to this Coinflip contract.
Can you write the address without the quotes?
Yeah,
just like that, or
it should be fine. I think it's probably. I think it should be fine. We'll see at compile time. If it throws an error, then I think it's okay. Let's check, because I think it's just declared as a string anyway because of the type. But I'll double check that, and the compiler and debugger will help me. I'm probably wrong, but I generally am. And so yeah, I'm declaring a type Coinflip where the contract is, and I'm going to say that it's the one that lives at my Coinflip address.
I suppose what I wonder, looking at this, is understanding the fundamentals of how you're thinking about constructing this, and like us having that same sort of fundamental understanding of, so that we're not, you know what I mean? So that we have that, I mean, even like after today, how we think about constructing these kind of contracts without, you know what I mean, without guiding, so we can, from a first principles understanding, we can think about how we can do that.
Mm-hmm.
I'm not sure if there's a good resource where we can go for that.
As I say, like the plugins that are available here in Remix itself, like LearnEth, are really wonderful. Because like you see, the interesting thing about like first principle thinking and this sort of stuff is that it arises from intuition, and intuition is generated by like bashing your head against the wall 100 times. That like 99% of success is just showing up, and if you're constantly like doing that, then you can develop an intuition about what the stuff is. As I say, like the best way that I have of explaining it right now at this point in my own like development in life is that, okay, we have these global variables that are being used in the other contract. Everybody has access to these global variables. If I can write the same logic as exists in this contract, then I can calculate what it's going to return before calling it, and preemptively send the right answer to the thing that I actually want to attack. And in order to do that, yes, I need to understand a little bit about Solidity, i.e. that I just have to declare this interface and tell my contract not just that there's this interface which defines the function that I'm interested in calling, but it lives at a particular address. And once I know that thing about an interface, and that there's this global notion of global variables available to everyone, everywhere, then I was like, cool, I'll just replicate the logic, calculate it myself. And then once I've done that calculation, submit the right answer to the thing that is supposedly ran. Does that help?
Yeah, a little bit.
it becomes easier with time, I promise.
I totally understand. Just sitting in that discomfort and just absorbing, and then eventually things connect. Yeah.
It kind of is the Turing equivalent of intuition, though, isn't it? Because every EVM instance everywhere is literally executing the same thing. So therefore, it's almost like a collective subconscious, isn't it?
Yes, exactly. There's a paper to be written on the EVM and Jungian archetypes.
Yeah.
I haven't got there yet, but maybe one day. Right? Future kernel adventure. It'll be fun. So yeah, we've understood these global variables. We've understood, okay, this interface which I've declared, and I've told my contract where it lives, and I've instantiated my interface at that address. And now I just need to write the function which is going to help me calculate what's already in Flip in this other contract, and send it the correct call. Right? So if I declare a function and I call it attack Flip, if I can spell, I can tell that my poor computer is really struggling. Brave is taking a lot of strain with all of this talk of Ramanujan integers, and Ramanujan summations, and the rest of it. Let's see if I can. Okay, we're taking a pause, a breather, while Brave decides whether it wants to work or not. Please forgive me. Can everyone still hear me?
Yeah, I can hear you.
Yeah, we can.
Yeah.
Please forgive the slowness.
Meanwhile, to answer Mark's question, like this is as first principles as it can get. Like Austin Griffith has built layers on top of this called scaffoldeth, which lets you build Solidity code without knowing so much details about the first principles. But yeah, this is how it's done. It's frustrating, but that's the only way to learn this.
Thanks, Sid.
Continue hoping for the best. Remix Ethernauts and Zoom at the same time is a bit much for my machine.
You can kill Brave and restart. It will be saved in your remix anyway, right?
I'm worried if I open my terminal, so then things will really.
It could be the YouTube tabs as well, and they in the background they suck up that huge resource.
All fall down.
You've got a couple of YouTube tabs there.
We need to get Andy some more RAM.
Absolutely.
Truly.
I'll donate to the Andy RAM fund.
I think he's frozen altogether now.
No.
Well, someone else could share their screen. I have my remix and I have all the code Andy has except the contents of Attack Flip.
Guillermo, you could share your screen, right? Or unless Andy didn't allow other people to do it.
Yeah,
No.
he might need to.
He probably not have enabled. Yeah. There he goes. All right, Afrida is now the host. Take it away, Afrida. If you want, you could give host or turn since you're host, Afrida, if you want to turn on, if you go to screen share, there's a little tilde next to it. If you want to turn on all participants, share the screen, and then Guillermo could share his screen. We could Can I keep the ball rolling while
Or
while we
Sid,
wait
or
for
someone
Andy to
that's
come back?
able
Or Sid?
to actually
Yeah.
write the function.
Well, how did I do that?
You see the
Share?
little arrow next to share screen at the bottom?
Yeah, but there are lots of buttons showing up here.
Yeah. So click the buttons, the two
Hello,
buttons that say
yeah.
all participants next to it.
Yeah, no, it's go on, share your screen. I think it will work now.
It should work now.
Yeah, it's working now, Guillermo.
Amazing.
Cool.
Yeah, here we are. So what should I write here? I have no idea.
Well, does Sid want to take it away? Sid, are you there?
So my guess is
Sid.
that we have to call.
Okay, we're back.
Oh, there you are,
I'm
Andy.
so
We're about to.
Surprise.
We were going full peer-to-peer here, decentralized Guillermo pulling up his
Amazing.
screen and showing us how to do this.
Amazing. Guillermo, please continue. Don't let me stop.
Yeah, so I'm just gonna calculate everything that the function is doing and just submit the result to this function that we're trying to attack. I have no idea if that's gonna work or how to continue from there.
Let's see.
Right function to
Ah,
do the
right.
bar.
So this just might need a little bit difference, but we can share both of our results and see that there are indeed many different ways to do things. As I slowly try and
So, but I don't know how to deploy it now using Remix, like how to actually call the function.
So there are a few things that I would like to change in this. Perhaps I'll start sharing my screen. The approach is right. There's like a few things that I would do just slightly differently. I'm back here. I'm gonna construct my contracts with my function with a guess that I'm going to pass to it. It's not exactly necessary to do this, but it just kind of helps me understand what I'm doing. As you did, I'm going to declare a UN256 for the block value, which
Hello.
is hello, which I'm going to get from Ethernauts. Coinflip contracts like you did, which is really incredible. The block value is calculated.
Battlefield. Whoa.
Elon, can you mute your mic, please?
Yeah. Sure. Sorry again. What's happening?
Don't be sorry, just don't talk with your mic on.
So block
No,
value
I see when
is,
it reconnects, it's gonna open the mic again. So I guess.
I'm going to declare my factor the same as I find in this contract. And you might be wondering, like, if this was a real environment, like how would I get access to my factor? That we're going to do, I think, in Force, in terms of looking again deeper into how Solidity handles storage and how storage actually works on the EVM, because there are ways still of getting so-called private variables by looking into specific slots. But for now, happily, we have what the factor actually is. And we're going to declare the Coinflip variable, I think, which we can let me think. The Coinflip is the same. The Coinflip is the same as the logic that we're doing in here, right? Which is this block value divided by the factor. We are not importing safe math here, so we can just have the Coinflip is block value divided by the factor, right? And then, just as you did, Guillermo, if we declare the bool side equal to Coinflip, which if it's 1, then true, otherwise false. That's shorthand for if-then statements. And what I'm going to say is if the side is the same as my guess that I passed in as a parameter, then I'm going to call my Coinflip contracts dot flip, the method there, with the guess that I made, because I know that it's the correct one. Otherwise, I'm going to call that same Coinflip contracts the flip method on it, and I'm going to do not the opposite of the guess, because the guess is either true or false. It's that Boolean. So this should calculate exactly the same Coinflip as what we're seeing in the contract that we're trying to attack. And if my guess initially was correct, then it will just send that guess on to the actual contract that I'm trying to attack and the actual method. And if my guess was incorrect, then it will send the opposite of that, which sort of by necessity is correct. If I change tabs from my file explorer to the next one down, which is the Solidity compiler, you'll see here that I can choose different compiler versions. That's going to be fine because I'm 0.8.0 or above. So even 0.6.0 above would work with this compiler version. I am choosing Solidity, not YUL, which is another whole thing. Oh my God.
Andy, aren't
Yes.
you gonna return something?
I don't need to return. I don't need to return anything from my attack thing. It's not necessary. I don't think. The return thing there is just because that's how the function is implemented in the contract that I'm attacking, and therefore I sort of need to have the same declaration in my interface. But for the function that I'm writing myself, I don't need to return anything. I mean, I know what the result is going to be. I'm devious and smart.
Andy, can you say again the block value? What the block value, the uint block value is doing?
The uint block value.
Uint
this,
to 56.
Line 13.
Yeah. So it's doing a number of things. First of all, it's looking at the current block number, right? Which is a big number on Ethereum at the moment. And it's saying, go and find the current block number, the block number of the previous block, right? That's what sub 1 means, like the block number of the previous block, and then give me its block hash, right? So remember in our, like when you see a transaction hash, there's also a hash for each block. And that ties into what we were talking about with Merkle trees, which is a longer discussion, but like each transaction has a whole bunch of information associated with it, which gets hashed together into the transaction hash. So using just that hash, you can know everything associated with the transaction. Then all the transactions in a block get hashed together, which is a particular kind of cryptographic function that takes a whole bunch of data and then returns just like a string of numbers and letters. And that string is like a fingerprint, which uniquely identifies all of the data in it. So all of the transaction hashes, which themselves identify all of the information associated with those transactions, get hashed. And that top hash is like the block hash, right? And from just that string, you can determine all of the different transactions in that block, and then all of the information about the different in each of those transactions. So it's a very efficient way of storing a lot of data in a very small representative space. So that's what we're like looking at there, is the block hash of the previous block. And block hashes are defined as bytes 32 types, which is like just a particular type of data. And we're casting that, which means like converting from the bytes 32 block hash to a 256-bit unsigned integer representation of the block hash. And that's like a really, really, really big number. It's in fact a number as big as this, but perhaps with like different digits. And so we're then able to take those two things and divide them by one another to see if we get 1 or 0. And because like the block hash is supposedly random, right? Because it is, like, nobody knows what the hash of the next block is going to be, because it depends on all of the transactions that get included in it and all of the stuff that goes on, and nobody can predict the future. So this is a supposedly random function, right? But it's not really, because we can access the same information in the block where this calculation is going on from any contract on the network. And so we can perform exactly the same calculation that the contract will perform and submit the transaction in that same block. And if we can do that, then we know that like that transaction that we're submitting, it's going to call the same logic that we've already calculated ourselves, figured out the answer for. And so we're calling it with like guaranteed the correct answer. We just need to add a public.
Thanks.
Sure. So we just need to add a public declaration there, I think. And
You have to change the sub with a minus sign.
Of course. Please excuse me. There's also something wrong in my declaration up there, which is strange. It's not enjoying that. Maybe there's something to do with the compiler version and interfaces that I'm not up to date with. These are the delights of programming, is sometimes don't really know the difference between 0.6 and 0.8, which I certainly don't, and therefore
change the public for external.
Yeah, that could work. Is it? I mean, Okay, let's listen to Guillermo and the message here, which is really revealing and wonderful. This is how we actually do things, but our remix is struggling again. Let's compile that. There we go. Okay, thank you very much, Guillermo. I really appreciate it. And we've got our compiled contract. I sort of hoped to go a little bit more into the details of this, but like it's really just the application binary interface, and you can look at like the bytecode that actually gets put on the chain, which is that object there, the different opcodes, which one day we'll get to, and various other things to do with your contract, which is really wonderful and is indicative of how awesome Remix is. Now that we have compiled it and we have something ready to deploy to a network, we can come to our deploy and run transactions tab, and you need to change your environment from the JavaScript VM, which is running on the site, the JavaScript virtual machine, to your injected Web3 provider, which is MetaMask, and you should be asked to connect. And once you do, you'll see it pops up with the Rinkeby network, which is a chain ID of 4, your account, and if all of that is in order, you should be able to deploy your first smart contract, which is kind of amazing. What I will do, I'm going to deploy this, And then I will drop the just while that happens. Just do this. Just do this. Okay, I don't want to publish all of these files. Let's see. I'll put this in the chat for those of you who struggle to follow along. If I can get the Zoom chat to come back. It's always there when I don't want it, never there when I do. It's a wonderful story of software in general. Okay, I can't get it to come back, excuse me. There we go. If you're looking for the just, which I will also direct you to the code for this kind of stuff afterwards in a more permanent format, but if you want the just, it's there. You can see that the deployment of my Coinflip contract has been successful. And I can tell because I have this attack Coinflip contract at an address on Rinkeby. So I've deployed my first ever contract onto Rinkeby. It's incredible. There's people celebrating in the background, a marimba band marching along the beach, glasses being crushed, plates being thrown, hopefully, roses streaming from the ceiling. If you've been able to follow this along from the start. And now what you need to do is call your attack flip function 10 times in a row. I'm not going to bore you and do that over and over again here in this tutorial, but you can sit and call this thing 10 times in a row. You don't even need to pass true or false to it. You can just, for instance, pass one. And if you call it 10 times in a row, you will get 10 correct consecutive guesses on your instance, which you'll need to change if you're using that guess that I sent. You'll need to change this Coinflip address to your instance that you got when you deployed this Ethernet contract. So there's my instance address, 0x7c5, which is what I've deployed. You'll change that. And if you call this attack flip 10 times in a row, then you should see that's you should be able to submit your instance, and off you go. So it's a little bit tedious to do that just on the call, but I've done it once, and just to check that it has worked, I can look at my contracts consecutive wins, and I have one consecutive win at the moment. So I know that I'm on the right track. And if I attack it again, then it should continue. Yes, Mark.
Where did you see that you had a consecutive win? Was it in the words? The array?
Yeah, I'll show you again now. Let's just because this can also happen because like of some particular bug in Remix. If you see this kind of error pop up, don't be discouraged. It's like got to do with gas estimation that's kind of going wrong on Rinkeby. Just carry on submitting it, and you should be fine. I was never really fully able to figure out exactly why, like some succeed and some fail. That's just it's like the same thing as a Riemann summation. I just put my hands up and wonder, okay, well, that's weird. But Mark, yes, here back in Etherscan, back on Ethernaut, where my instance is waiting, if I now call consecutive wins, I should have 2, and it's in this words array, and it's 2, right? There's 1 consecutive win and 2, and when I get up to 10, I should be able to submit my instance.
Yeah, it's weird that it labels it as like words. It's like kind of, because you would think it would be this number that's right next to the brackets, right? When you do a weight and it shows like a 0 that's white, you'd think that number would be the number. It would just tell you exactly how many consecutive wins without having to like infer of like, oh, it must be in the words thing. You know what I mean? It's a bit confusing. It's not as like straight. It feels like it's not as straightforward.
It's it's a artifact of the fact that it's hexadecimal data on chain, and it's these really big units, these 256-bit numbers that JavaScript is kind of like famously bad at processing large integers, and so this is like it's an artifact of like trying to get a 256-bit virtual machine to speak with like ordinary people's code. There are many deep and nerdy discussions, particularly on Reddit, about the choice to make the EVM 256 bits, because, you know, like at the moment I'm on a admittedly very shitty but 64-bit machine, which most of us will have, right? And that's kind of the standard. You have also 32-bit machines, much easier to handle numbers and this kind of stuff. But the EVM, like 256 bits, because it corresponds to some of the cryptography and it makes those kinds of calculations a little bit easier. But it means that this sort of stuff, like fetching balances and simple numbers stored in storage, whatever, is more difficult. So yeah, it is unintuitive, but the big number library helps a lot with that. And recently, like, it's no longer accessible. Web3.eth.bn used to give you what you needed from MetaMask, but it seems like they've removed that library from their provider. It's very easily accessible, though, when you're writing your own front-end code. Big number is there. I'm sure people like Paolo will have lots of fun experience with big number, to hex, to ASCII. Oh dear. Thank you for sticking it out, everyone. If there are more questions, I'm willing to answer them. Office hours is happening now, if you want to go there too, but I'm here. If you want to commiserate on how unintuitive some of this stuff is, I'm also available.
Thanks, Andy. I'm going to jump to office hours. Appreciate all your help.
Thanks, Andy.
Thank you.
Guillermo, thank you so much.
Thanks, everybody. See you soon.
I appreciate you stepping in there.
Someone had to do it.
Truly, that's how it is. You know, that's what these environments are. It's not me, it's someone else. Right?
Thank you. See you.
Thank you.
Bye.
Thank you. Go so well. Enjoy your day.
Cheers.
Thank you.